Hello, everybody. In this brief slide presentation, I want to talk a few things. I want to talk a little bit about some of the properties of heuristic functions that we need to know about. We're going to look at two properties. One of them is informedness, and the other one is admissibility. So informedness is how good is the heuristic? How well does it direct us to the goal? How goal-directed it is? Now, to contrast this thing, let's assume that the heuristic always returns 0. In other words, it's very optimistic. It always thinks, we're there, we're there, we're there. However, if you think about it, this really brings us back to uniform cost search. We're just going to completely ignore the straight line distances, and we're going to go back to those concentric circles, right? So that would be pretty bad. The way, and again, there are, for some of the domains, different heuristics that we can look at, and some of them are more informed than others. By and large, the more informed the heuristic is, the more CPU time it takes. So there's a little bit of a trade-off with developing a dynamite heuristic versus letting the search algorithm do all this stuff. There's one thing I can tell you, though. Your heuristic should never be doing search. If you find yourself doing search as part of your heuristic, you're on the wrong track. All right, just turn around, go back, go somewhere else. The informedness then can be visualized as sort of like the width of these ellipses, right? The wider they are, the less informed they are, the more narrow they are, the more informed they are. Now, the next thing we're going to look at is admissibility, and that's sort of like a crucial property. Every heuristic that we come up with has to be admissible. That means it can never, ever, ever overestimate. It always has to underestimate the remaining cost. So notice that as the crow flies, always underestimates the remaining cost because, you know, even if we have straight roads like some of the interstates in the north and in the far west, you know, just they're straight as you can see. I mean, just not a curve inside, right? But even then, I mean, they underestimate, right? Because it has to be smaller equal to the actual distance as the crow flies. Again, if you've driven in southern Indiana or any of the big cities or in the east, well, you know that the roads are not exactly straight as an arrow. So clearly straight line distance does underestimate. By the way, my wife and I have a 2014 Honda Odyssey, and the navigation system on it has a very interesting feature. It has this pink line. And the pink line actually shows you the straight line distance to your goal. So it's sort of like, do you feel like roughing it? In which case, just drive through this farm field here right now and you'll be at your goal, well, at least in a lower distance, right? So it's pretty interesting. I thought that was kind of cute. So clearly they use straight line distance for some of this stuff. So let's have a look at this following example that we looked at when we looked at A star. So this is the last step where we picked Bucharest, but I want to look at the second to last step where we expanded Pitești. So suppose that our heuristic overestimates, and in particular, assume that the value that is returned for Pitești is 150. So rather than 100 as we see over here, we get 150. So if we add that to the 317, then we have the overall value of 467. So Pitești would be put onto the priority queue with a value of 467. For argument's sake, also assume that the heuristics from Timisoara to Bucharest and Zărin to Bucharest add 5 each. So as you can tell, where I'm going with this thing, all the values then will be larger than the one to Bucharest, right? So 467 is larger, at 5, you know, what is that? 452, 454, they all will be larger. So what's going to happen? The next time around, we are going to poll our priority queue and we'll get Bucharest, right? And so that means we are missing the optimal solution, which goes through Sibiu, Râmnicu, Vâlcea, Pitești, and Bucharest. So that's what you get if you overestimate. If you overestimate A star or not, you're not guaranteed to find an optimal solution. All right, that's it.